Hello everyone. We are discussing on the subject electromagnetic theory. In that we are discussing magnetostatics. So under the magnetostatics, the last and final topic we are discussing is inductance. In inductance, again I divided the topic into three topics. So the first part is nothing but what is definition of an inductance and what are the two type of inductance, self and mutual inductance, and analysis of that self and mutual inductance, and some important points to remember, like for example coefficient of coupling, if connections are if the coils connected as a series opposition or series aiding, then what is the expression for equivalent inductance. All these steps we have already discussed in the part 1 video. Now in this part 2 video we are going to concentrate on the applications of inductance. Hi, I am Nageshwari, Assistant Professor, Department of EEE RMK College of Engineering and Technology. So let me check the video. Okay, so this diagram is nothing but what? It is nothing but this solenoid diagram. Yes. So we are going to consider the first application as inductance due to solenoid. So it is a very simple, each and every applications I am going to derive as a simple expressions only. Okay, so first we are going to see about a solenoid. Now what is that? So consider a solenoid of n number of turns carrying a current. Okay, of n number of turns carrying a current I. So again, if B is the flux density and A is the area of the cross section, then the flux linkage is given through the solenoid is given by, you know very well what is the flux linkage. So what is the flux linkage? So phi is equal to B into A, right? So therefore N phi is equal to N into B into A. Okay, since phi is equal to B into A, so therefore we can say N phi is equal to N into B into A, right? So now we know very well the self inductance formula is given by L is equal to N phi by I only. Know what is N phi according to the above equation. What is your N phi? N phi is equal to N into B into A by I, right? Okay, N B A by I. So but for long solenoid, we already discussed for long solenoid what is your B expression or what is your H expression is nothing but B is equal to mu naught into Ni. Okay, so mu naught is equal to Ni by L. Okay, so mu naught is equal to, so this is nothing but L. Okay, so this is nothing but it is so this is nothing but L. Okay, so this is nothing but L. Okay, so mu naught Ni by L. So this is for long solenoid. So for long solenoid we already derived all these things. So for long we already known all these things. For long solenoid B is equal to mu naught into Ni by L. So substitute the value of B in the above equation. You need to substitute this B in this expression. So now what is your expression? L is equal to what? Na by I into mu naught Ni by L. Now if you multiply n into n square, then finally what is your answer? Mu naught, this I and this I will get cancelled. Then finally what is your expression? L is equal to mu naught into n square A by L. So therefore the inductance due to solenoid is given by the expression L is equal to mu naught n square A divided by L. So this is called as the expression for the inductance due to solenoid. This is the first application. Now the second application. The second application we are going to see is nothing but the inductance of a toroid. Okay, now consider a toroidal coil as like this. Consider a toroidal coil as like this. So consider a toroid of n number of turns carrying a current I with the mean radius of R as shown in the figure. Okay, carrying a current I with the mean radius R shown in the figure. If B is the flux density, suppose the B is the field. B field is in the flux density. So we know very well what is B. B is equal to mu naught into Ni by L, right? So where L is nothing but what? A mean length of the coil, right? Okay. So what is mean length of this coil is nothing but what? To L is equal to 2 pi r. That is nothing but the mean length of the coil. Okay. So L is equal to 2 pi r. Okay. Now therefore what we can express, so B is equal to mu naught into Ni divided by 2 pi r. So this already, this toroid and etc. already we have discussed in my last videos, that is H due to toroid. What is that H due to toroid? Everything, all these applications, the magnetic field intensity applications I have already discussed in my previous videos. So if you want, you can check it out at my YouTube channel. Okay. So B is equal to mu naught Ni divided by 2 pi r. So also we know the flux linkage in the toroid is nothing but N into phi. So we know very well phi is equal to B into A. So therefore N phi is equal to N into B into A, right? So what you need to do, you need to substitute this B in this equation. So N phi is equal to Na into mu naught Ni divided by 2 pi r, right? So therefore N into N is nothing but what? N square. So mu naught N square Ai divided by 2 pi r. So where A is nothing but the area of the cross section. So if R is the radius of the coil, suppose say for example, if small r is the radius of the coil, therefore the area is nothing but pi r square, right? Okay, the area is nothing but what? Pi r square only, no? So therefore instead of A I can substitute pi r square. Okay, instead of A I can substitute pi r square. So therefore mu naught N square I into pi r square divided by 2 pi r. So therefore mu naught N square r square I divided by 2 into r. Okay, so where r is nothing but the mean radius and small r is nothing but the radius of the coil. I repeat once again, the capital R is nothing but the mean radius and small r is nothing but the radius of the coil. Okay, so therefore the inductance of the toroid is given by the expression L is equal to, so mu naught into N square r square by 2 r. So why? Because you know very well L is equal to N phi by I only, no? So therefore N phi by I is nothing but self inductance is nothing but what? Mu naught N square r square by 2 r. This is the expression for inductance of the toroid, where a small r is nothing but the radius of the coil and capital R is nothing but the mean radius of the coil. So that is about the second application. Now the third application. The third application, again the third application has two parts. Okay, the first one we are going to see, the third application is actually a coaxial cable, but the coaxial cable application also we are deriving as a two parts. Okay, the first one, now we will see the ordinary coaxial cable. Okay, that is let you forget about that inner conductor, outer conductor, like that. Okay, you just a long coaxial cable. So assume a long coaxial cable. So in that first you need to find out what is inductance. Then the second part is nothing but you need to include that inner conductor and outer conductor concept. Then what is the inductance? Okay, so the both the parts we are going to discuss as a coaxial cable derivation. Okay, let me check the first one. Consider the coaxial cable of inner radius A and outer radius B as shown in the figure. This is a general a coaxial cable one, but the first part we are going to see as a general part. Okay, so consider a coaxial cable of, this is the inner radius A and the outer radius is B. Okay, let I is nothing but the current in the inner cylinder and minus I is nothing but the current in the outer cylinder. Now consider an annular ring of thickness. Okay, this is annular ring of thickness is nothing but dr at a distance of r meter, at a distance of r from the center of the cable, at a distance of r from the center of the cable. So the flux density B is given by, so we know very well what is the H due to long conductor. Okay, so this coaxial cable is similar to your H due to long conductor. So therefore we can get the H due to long conductor as as an example here. So B is equal to mu naught I by 2 pi r, mu naught I by 2 pi r. Now therefore in general case we are solving first part as a general case, right? So therefore the total flux linkage per unit length between A to B, that's it. Okay, so between A to B is given by the expression. So phi is equal to what? Integration of A to B mu naught I by 2 pi r into dr, right? So mu naught I by 2 pi r is nothing but as a 2 pi r is a constant. What is integration of dr by r is nothing but ln r. So ln r and the limits is A to B. So therefore ln B minus ln A will come. If you apply the limits, ln B minus ln A will come. Therefore ln B by A. So therefore phi is equal to this is the flux phi. Now what is your inductance? L is equal to phi by I, right? L is equal to phi by I. So therefore L is equal to, that is the inductance of a coaxial cable, general inductance of a coaxial cable between A to B. Okay, between A to B, the long coaxial cable between A to B is given by the expression L is equal to mu naught by 2 pi into ln B by A. So this is the general inductance of a coaxial cable. So okay, first part. Now let me check the second part. Now what is the second part? So second part is nothing but you need to consider with the solid inner conductor also. Okay, you need to consider the solid inner conductor also. That is your second part of the coaxial cable. Okay, that is the heading of this derivation is nothing but inductance of a coaxial cable with a solid inner conductor. Okay, let me check again the same diagram only. So you need to check again the same diagram only. So consider a coaxial cable with a solid inner conductor of radius A and outer radius is B. Okay. Now let I be the current in the solid conductor and minus I be the current in the outer conductor. The flux density within the solid conductor at a distance r from the axis of the cable is given by what? So B is equal to mu naught mu r I dash. Okay. So I dash r divided by 2 pi a square. So where this r is in between 0 to a. Okay, so this r is in between, okay, so 0 to a. This r is in between 0 to a. Okay, so therefore the current flowing in the inner conductor, okay, the current flowing in the inner conductor between A to R, okay, so between A to R is given by the expression I dash is equal to, so I dash, so here what is that I dash? So I dash is nothing but the current flowing in the inner conductor between A to R. So you generally here there are two currents. I repeat once again because there will be some confusion among this current part. That is why I am repeating the current part once again. Let plus I be the current in the solid conductor, inner, okay, solid conductor, solid inner conductor, whereas the minus I be the current in the outer conductor, right? So now what is that solid conductor means? Okay, inside that if you see here, so if you see here, this is nothing but the inner part of the outer conductor, right? So therefore this plus I and minus I. So now if you realize that what is plus I and minus I, okay, so this is the outer part and this one is nothing but the inner part. Now what is the I dash? So I dash is nothing but a solid inner conductor between A to R, okay, between A to R, then the current flow expression is nothing but I dash. Okay, so what is I dash? What is I dash? So I dash is nothing but so pi I by pi a square, that is nothing but what? So I by pi a square into pi r square. It is nothing but I is equal to j dot ds, no? So that concept only here we should take. So you know very well I is equal to integration of j dot ds. Okay, so we know very well. So I is equal to, okay, so integration of j dot ds. ds. Okay, integration of j dot ds, or we can say, so j into integration of ds. Okay, so this the similar concept we already discussed h due to coaxial cable. The same concept only here repeating. Okay, the concept will not change. The coaxial cable concept will not change. So you should remember that first. Okay, so actually I is equal to integration of j dot ds. So j into integration of ds. So what is this j? This j is nothing but the current density. Okay, current density of the conductor, and this integration of ds is nothing but the area of the ampere and path. Okay, area of the ampere and path. Here what is the area, radius of the ampere and path? The radius of the ampere and path is nothing but pi r square only, no? So therefore this is nothing but the integration of ds part. Nothing but the integration of ds path. Okay, so what is this integration of ds? Is nothing but the area of the ampere and path. You know what is the area of the radius of the ampere and path is small r, therefore pi r square. Now what is this part? So this part is nothing but what? J. This is nothing but what? J. This is nothing but j. So j into integration of ds. So now I think if you understood the concept, right? Okay, so this I dash is nothing but the solid inner conductor between A to R. So therefore here again the concept as I is equal to integration of j dot ds concept will come into the picture, and now everyone understood that what is that j and what is that integration of ds. Okay, so therefore I dash is equal to, if you cancel out this pi and pi, then finally what is your answer? I dash is equal to I into r square by a square. Now what is your b? Substitute. Yeah, now you need to substitute what is that I dash. Okay, so what is that I dash? So mu naught mu r by 2 pi a square into what is your I dash? I r square by a square. So finally if you substitute mu naught mu r cube divided by 2 pi a power 4. If you simplify this, then we can say, so 2 pi into a power 4. Okay, we will repeat that in this slide. So the total flux per unit length between 0 and a is nothing but what? So phi is equal to, so integration of 0 to a. So now you need to apply the limits, right? Okay, so that is why. So phi is equal to integration of 0 to a mu naught mu r cube divided by 2 pi a square into dr, right? Okay, so you need to integrate with respect to dr. Okay, so r cube into dr is nothing but what? R power 4 by 4, and you need to apply the limit. Is nothing but what? A power 4 by 4 minus 0 by 4. So a power 4 will get cancelled. Then finally what is your answer? So phi is equal to mu naught mu r I by 8 pi. So this is the flux linkage between A to 0 and A, right? Okay, so therefore the inductance of solid conductor between 0 to A is nothing but what? L1. So therefore let this be L1. Okay, let this inductance be L1. This inductance be L1, we can say, right? Okay, so L1 is equal to mu naught mu r divided by 8 pi. So this is between 0 to A. Okay, now what is the next part? See, actually the solid actually this coaxial cable is you have inner radius is A and outer radius is B, right? So now what you need to do? So you need to consider the general case. Yes, of course, you need to consider the general case of an inductance of a coaxial cable. Okay, so we know that the inductance of coaxial cable per unit length between A to B also we need to consider, right? Okay, so between A to B is given by the expression L2. Let that be L2. So L2 is equal to mu naught by 2 pi ln B by A. We already discussed this expression in the first part, right? Okay, now what you need to do? You need to find out the total inductance, means you need to add up the total L1 and L2. So therefore L is equal to L1 plus L2, L1 plus L2. Now if you substitute and if you add up these two expression, then finally what is your inductance? L is equal to mu naught by 4 pi into half mu r plus 2 ln B by A. That is about your inductance of a coaxial cable, both general case and as well as the inner solid conductors. Okay, Now, that is about the third application. Now, the fourth application is nothing but the inductance of the two transmission line. Okay, so inductance of the two transmission line. Now consider here also again there are two conductors A and B. You need to find out what is the inductance of A and what is the inductance of B. Then finally you need to add up these two inductance. Then the final expression will come. Okay, now let me check. So the two conductors of named as A and B, who's having the current as plus I and minus I respectively, and these both are separated by a distance t. Now consider two conductors or wires. We can say A and B of radius A and B, small a and small b. It is nothing but radius of the two conductors respectively, and it is separated by a distance t. The conductor A, now let me check the first conductor, the conductor A. The conductor A carries a current of plus I and conductor B carries a current of minus I. Now, the internal flux linkage of the conductor A. Now, what you need to do? You need to find out the internal flux linkage of conductor A. The internal flux linkage of the conductor A is given by phi 1 is equal to mu naught mu r I by 8 pi. So, how it come? It comes from the previous derivation only. So previously we have discussed, so coaxial cable, the same concept only here also it can applicable. Okay, so therefore phi 1 is equal to mu naught mu r I by 8 pi. So the external flux linkage with the conductor A is given by the expression phi 2 is equal to mu naught I by 2 pi into ln d by a. Instead of there in my previous coaxial cable inductance of coaxial cable expression, no, so the same concept only here also we need to use. Okay, there the limits is b to a, but here the limits is d, that is a distance d, that is only the difference. Okay, so therefore what you need to do, the total flux linkage of A is given by phi is equal to phi 1 plus phi 2. Now if you both add up these two expressions, then the total inductance of A is given by the expression LA is equal to, so mu naught by 4 pi into mu r by 2 plus 2 ln d by A. This is the inductance of a conductor A alone. Now what you need to do? You need to find out the conductor B. Okay, you need to find out the for conductor B. So for conductor B, again the total flux linkage is given by phi is equal to same mu naught mu r I by 8 pi. Okay, so by 2 pi into ln d by a. So for conductor B also the same. Okay, the conductor B also the same concept only. Okay, so now what you need to do? So you need to add up these two expressions. L is equal to LA plus LB. So if you add up these two expressions, then finally your answer is, if you simplify 1 by 1. So if you simplify 1 by 1, then finally your answer is L is equal to mu naught by 4 pi into mu r plus 2 ln d by a the whole square, or we can say L is equal to mu naught by 4 pi into mu r plus 4 ln d by a. So now so in this video, so we are totally discussing on the applications of the inductance. So under that, the first application we have discussed is the inductance due to solenoid. The second application we have discussed is nothing but the inductance of a toroid. The third application is inductance of a coaxial cable. That inductance of coaxial cable also we have discussed as a two part. One is nothing but the general case, that is nothing but between A to B, and the second one is nothing but the consider the solid inner conductors also we have considered, and we have discussed about the inductance of the solid inner conductors also. Then the last one we have discussed is nothing but the inductance of two parallel conductors. Thank you all. Thank you for watching this video.